All right, so cursive dimensionality, this is the overview, and generally this set of notes is about just some thoughts about the cursive dimensionality and some strategies for confronting it. This is something that I think is really important, especially when you're thinking about using particle filtering techniques for doing state space tracking, that I think isn't adequately discussed in the literature and the books on this topic. And so, disclaimer, this set of concepts is not something that I've really drawn from the literature. This is largely my own thoughts. It's not out of the papers and based on my own experience and ideas. And there's some things here, as I mentioned at the outset, there's some aspects of this that I don't fully grasp or understand myself. So I'm hoping we can have a bit of a discussion about this, and I'll point out the things that sort of interest me about this. Let me start off with just a review of some of the concepts. It may also be helpful for preparing for the quiz on Wednesday. With generally speaking, state space tracking, or what I'm titling in this slide Bayesian tracking, because we're using Bayesian techniques throughout. We're assuming the thing that we're trying to estimate is itself a random variable, and we've got some prior information about it. We usually want to estimate either what I'm calling the marginal posterior or the joint posterior, where the marginal posterior is just what's the distribution of the state at the current time given all the observations we've seen from time 0 up to the current time. I know I haven't been able to cover it in this class, but I know Dr. Wan talked a little bit about smoothing, and there are related techniques where you talk about what if this is n plus some number, where you're using future data as well as past data. And there's a number of things that go into that, but I can give you more reading on that if you're interested. So this is the marginal, because we're just trying to estimate the state at a current time, or at least get the posterior of the state at a current time. And this is about the entire trajectory. So rather than just the state at time n, we're interested in the posterior of an entire trajectory from time 0 all the way up to the current time. So that's the difference between these two, and we've talked about both a lot. Most of the methods are focused on this. The Viterbi algorithm actually was more focused on this, but they're both important conceptually. And all of the state estimates that we generate essentially come from one of these two posteriors, whether you're talking about the extended Kalman filter, unscented, linear, one of the particle filtering techniques. They all are unified by this idea of providing an estimate of something, a mean, a median, a mode, of one of these two distributions, one of these two posterior distributions. And usually it's this one. The only one that used this one so far has been the Viterbi. Just be review. And because we're talking about the cursive dimensionality, it's worth thinking some more about these two. Both of these are a PDF, which means that they produce a single number. For a given set of observations, if you could evaluate this at a given state, you would be feeding into this, assuming the observations are given, so treating this just as a function of the state. This would be then something that maps something of dimension n sub x, I'm using that to represent the dimension of the state vector, to just a single number in this case, a single real number. And this has a much bigger argument than this does. I'm trying to remember the mathematical terms. You were just talking about how you've got a strong math background. I think the dimension of the argument is called the domain, and the dimension of the function, in this case it's scalar, is called the range. Is that right? Am I using the right terms?
Codomain.
The what?
Codomain.
Codomain?
Yeah, you can use that too.
Okay.
But I think range is common.
Yeah.
Okay, so domain and range. So the dimension of this domain is weird to think about because it grows with time. At every given sample, we've got n plus 1 samples here. We've got a state vector of dimension nx, and so the dimension of this thing is just getting bigger and bigger and bigger. It's growing linearly with time. So the joint is this really high dimensional thing, and the marginal doesn't grow with time, but it still can be very the design of your state space model. And There's a lot has been written about this thing called the curse of dimensionality. I think the person who coined the term was Bellman back in 1961. And it's something that a lot of statisticians and engineers that do the kind of work that we do, data analysis, signal processing, control systems, have given a lot of thought to, and it's important. One of the things to consider is thinking about when we're trying to get an estimate out of one of these two posterior distributions, whether we're estimating a mean or a mode or maybe a percentile or a measure of variation of some sort, we should think about how is this growing? How is this getting harder as the dimension of the argument grows? And that's important for us to have a grasp of because it gives us insights about how to tune the models and how to design the models we're working with. You can always make the models more complex, but as you make them more complicated and you increase the dimension of your state vector, what are you losing? How much harder is the problem to track? There's a trade-off there that you have to consider. So think, for example, let's just say that we were doing map estimation, and what we're trying to find is the peak of one of these functions. And let's say that we don't have a good way of doing the optimization. We haven't talked a lot about optimization in this class, but generally high-dimensional optimization is a hard problem. And if it's nonlinear and there's multiple modes and you're searching for a peak, but there may be many mountains in your space, it's a really hard problem. And there is no global optimization algorithm that works for any nonlinear optimization criterion. You could take a whole class on this topic. But the point I want to make now is that as the dimension grows, it gets harder and harder to find that peak, and you have to explore more and more of the space and expend more and more computation, spend more cycles. So if we're doing map estimation, we've got to find the maximum. Let's say we used a uniform grid. If we had just one dimension, if our state was just one dimension, then we could imagine, let me do it this way. You can imagine sort of maybe filling in 10 points along your grid, that I'm denoting sort of as hash marks. And you might say, okay, 10 points is sufficient, but if I'm just searching along one dimension, I'll find something that's close to the maximum. If you go to 2 dimensions and you want to do the same thing, though, now you've got those same 10 hash marks, let's say, change color again. Sorry to change color on you, but I think you can take it. So let's say we have the same 10 hash marks here, but that's only one row. We need to go up sort of 1 and get another 10, and then up 1 and get another 10. I know this isn't 10, but it gets the idea that the number of points that you need as soon as you go to 2 dimensions is much larger than what you needed in 1 dimension. Now we've got 10 here, but we've got 10 rows, and so it's 100 points that we need rather than 10. And all of you have enough math that if I drew a z-axis there and we thought about filling a 3-dimensional space, it'd be 1,000 points. So it increases by a factor of 10 with each dimension. And that idea generally is true. If you want to explore a space densely that has dimensions with, let's say, a grid that has n sub g points along any dimension axis, then as your dimension grows, it grows exponentially. And that makes it really hard. I mean, even getting to 3 dimensions, 10 points is not a very dense grid. I mean, normally if you're looking for a maximum, you would probably want more than that, depending on how sharp your modes can be. But if you had 100, now you're talking about 100, 2 dimensions, it would be 10,000. In 3 dimensions, you're at 1,000,000. And we're working with state space models that often have dimensions that are 10, 20, 30 dimensions. So I mean, you can't get there. You just simply run out of dimensions if you were try to densely fill that space. You can't fill it, and that's sort of the essence of the curse of dimensionality. That problems get exponentially harder, usually as the dimension increases. And the thing that's been puzzling to me is very early in the term when we were talking about Monte Carlo integration, And we said, well, we can express an integral as an expectation, and we can approximate an expectation. This is just a mean of some function. And we can approximate a mean as being a sum of points, a sample average. And the sample average gets better and better as we have more points. The notation's inconsistent here. This should be n sub p, where it's however many points we're using in our sample to calculate this average. But this converges is order 1 over n, and the thing that's really surprising is that this was independent of dimension. Now, how did he get away with it? How did you suddenly beat the curse here, where it doesn't matter if this is a 5,000 dimensional space or one-dimensional space, the rate of convergence is the same? And what happened there? To me, that always sort of bothered me. It seemed like there was something that wasn't quite right about that worthy of some more thought. I just simply didn't understand it. And if we study carefully what went into the particle filter, I think we can begin to get some clues on where things aren't quite right. So with if you could do it perfectly, this is how you would do a prediction step, this is the filter step, these are the optimal recursions that we had. And when we're using traditional particle filters, one of the things that we had, I've really got the wrong equations to make this point, but it's not going to let me. But with traditional particle filters, let me erase that, that's going to drive me crazy. Okay, sorry. With traditional particle filters, what we're estimating are moments. We could estimate the mean, we could estimate a variance. From the variance, we could get the standard deviation. We could do expected values of nonlinear functions of the state. But we couldn't do percentiles, we couldn't do the median, we couldn't do the mode. Those things are, we sort of had to finesse with particle filters, where we would estimate the density. As soon as you try to estimate a density, you're actually running into the curse unless you make some assumptions that we made, and it's usually a bad idea. So usually with the traditional particle filters, we're limiting ourselves to these things. And where particle filters, in my mind, really shine is when you've got multimodal distributions. If it's multimodal, then arguably the mean isn't the best choice, as we've talked about. Probably the mode or something else is usually what you want. The mean may be an improbable value. So this was one limitation, and this is one reason why that limitation is unacceptable for the types of problems where you'd want to apply particle filters. The second, and in my mind the killer, is that we can't draw samples from the posterior distribution. A, we don't know what it is, and B, even if we did know what it is, that doesn't mean that we've got a random number generator that we can use to draw samples from the posterior. We can't. And so we found sort of a way around that. That's what led us to use the so-called importance density, which led us to use a weighted average rather than just an unweighted average. And then the weights became unequal, and we found other problems associated with that. So same 2 points in the previous slide. When we're working with this sort of thing, with particle filters, we're limited to moments, and that's one. And secondly, we can't draw samples from the posterior. So if we could do those things, then arguably it would beat the curse. And it beats the curse. How does it beat the curse? I'm not certain. This is one of those cases where it's the edge of my knowledge. But I think it beats the curse because you don't need to densely sample the space where there isn't much density anyway. And this gives you that insight as to where to put your points and where really not to put your points, where you don't need to. You don't have to scatter them everywhere. You only need to put them where that probability is concentrated. And if you do put them everywhere, if you had a uniform probability that was your posterior, if that was uniform, well, first of all, you're not going to be able to estimate the state very accurately, but even if you could, well, I guess I just don't know in that case why a nonlinear estimate of the state wouldn't matter so much where the points were located. I don't know on that.
I'm just wondering if it's that big O notation that's
No, it's not there.
I mean, for a particular instance, you say that as you add more particles, it's big O of 1 over n, but there's a constant factor in that, right? And that constant is constant for that instance, but it might be exponential if you consider different.
Yeah, no, I'd have to go back and look at that now and the conversions, but I'm 99% certain that if you go back and look at it, the constant factor that you're referring to, the lower order terms, are still independent dimension. I think that's true. Yeah, it's a good thought. I mean, it's a good idea, but I don't think it's right in this case. Where we really saw the curse of dimensionality sort of rear its head with the traditional particle filters is in these weights. You know, we can't draw from here. We can draw from here, but we're kind of guessing. You know, we're trying to make this as close to that as we can. But when you are in an extremely high dimensional space, trying to get this to match up with that is really difficult. It's really easy to go places where the state is not, where it's very improbable. And as soon as you do that, where Q has a much larger value than P, your weights just plummet to 0, which is what we all experienced as we went through the exercises. So with importance density, the idea of being able to draw enough samples or just generating far more maybe than we need, so we have enough particles, we're just throwing away clock cycles if we've got a lot of weights that are 0. And it turns out that all the weights are headed towards 0. Fortunately, they're normalized, but then we only end up with one that's dominating. And keep in mind, when we look at it from this perspective, we're trying to draw samples from a distribution that's different than this, but is kind of like that in a dimension that's growing with time. And so this problem gets harder and harder as time goes on, which, again, we witnessed as the so-called degeneracy problem, where we end up with only one particle contributing to our estimate very rapidly. And I think this is just a manifestation of the curse of dimensionality. We've talked about this idea before, you're all familiar with it, you've all experienced it. But what is a little bit different than the literature and what we talked about before is that here I'm putting it in the context of what's driving that is not so much that there's a mismatch between these two, as much as it is that it's hard when you've got such a high dimensional space to pick particle trajectories that are probable, because you're in such a high space. It's just hard to find these points where Q matches up with P, essentially, and our weights stay large. So it's that concept that's a little bit different.
This is actually a slight sidetrack, because it's mostly relevant to a problem I was looking at, where there isn't a lot of variation in the states over time. They're almost constant, but they're very narrowly defined. You know, there's not a lot of variance in the initial state, and you know, that's the big question. It doesn't change much. It's kind of like estimating a parameter, I guess. In that kind of situation, I think this is what was causing me problems in getting good results there. Is it done, and it looked like something that was done in some of the papers you gave us, when you do this importance density, is it ever done where you take some portion of your importance density and you have it, I guess, equal to your state transition density that you suppose, and then taking another part of it and just, some portion of your particles and just scattering them at every time step, just, like in a grid? I know that's kind of done in the Turby particle filter, sort of, but do you ever just kind of use a mix of two different importance densities?
Yes. So two responses. The first one is, if you've got a problem where your measurements depend on a parameter that barely changes, or maybe doesn't change at all, but you don't know what it is, one way of handling that is to fold it into the same framework, and modeling that as, you can model it as a random walk with a very small noise, so it changes very little, or you could even model it as a constant. Say, here's a parameter, and its process model is that at time n plus 1, it's equal to what it was at time n, with no noise. You could do that, especially in a particle filter framework. And you say, well, how does it estimate it? And the answer is that you initialize it with very large uncertainty. So within a few samples, it figures out what it is, and then it essentially keeps it at that value from that time forward. And that's a perfectly reasonable thing to do. So if you have an unknown parameter that is constant, you can still fold it into this framework. It may not be the most efficient way to do it computationally, but people have done that, we've done that, and it's fine. We do that with the mean heart rate. My mean heart rate's different than yours, and it's different than everyone else. But once I know what your mean heart rate is, the fluctuations tend to stay really close around that mean. And so that was an example where we used exactly that approach. We folded it in and we allowed it to change, but on the scale of hours rather than what the fluctuations are about that mean. So that's one answer, is if you've got an unknown parameter, that's a reasonable way to handle it within the framework we discussed. The second, the idea of the importance density really being made up of two distributions, where you've got one where maybe you're using one of the importance densities that we talked about in the lectures, and then you've got another one that's just trying to scatter the particles all over. Some people do that to handle the problem not of degeneracy, but what I actually have on the next of sample impoverishment, I think is the term that's used. No, it's not here. Oh, it is, sample diversity. Sample impoverishment, it's different terms to describe the same idea. The idea is that if you use traditional particle filters, all the particles end up gathered around the modes, just as we've all experienced. And then you're blind. You don't have any particles in a portion of the space where something may pop up or something may occur. And so scatter your particles, reasonable approach. The difficulty is that it's hard to scatter your particles when you're in a high dimensional space, for exactly the reasons we talked about. You can't do the uniform grid. In the example I had of the car tracking, where there was a uniform grid of the Viterbi, and it looked, oh, great, it's covering any place the state could be, and it seems like it's doing a really good thing there. It works well in one dimension, but in 5 and 10, it becomes hopeless, because for the reasons we were talking about before, you just can't densely sample that large a space. Even if you say, well, I'm just going to do it uniform and use as many particles as I can afford, you can do that, but ultimately what that means is you've still got a lot of holes where you're just not going to be able to cover it if you're in a high dimensional space. So, so it is done, but I don't think it's a very effective strategy. We did resampling to handle the issue of sample degeneracy, where a lot of the weights went to zero because we had improbable trajectories. And that eliminated the trajectories or the samples of the particles that had low importance weights. One of the things that I didn't discuss at the time, if you dig a little bit deep, the theory, the math of particle filters can go really deep, much deeper than we've gone in this class. And if you start to look carefully at the convergence proofs for particle filters in this order of 1/n that we were talking about, when you do the resampling, technically your samples are no longer independent of one another. You've now created a dependence. If I have an idea of what one particle is and I've resampled, then I have an idea of what another particle is, because I know that there's been this sampling with replacement, and so odds are that another particle is at that same exact state now that I've done the resampling. And so the convergence proof that generated that 1/n result is now broken. One of the assumptions of that is broken. There are other convergence proofs that say, well, if you've got enough particles, even when you resample, you can still argue that there's some independence there and it does converge ultimately, but these are weaker and converge less rapidly. Sam?
What's that square root of that?
It depends on whether you're talking about the variance or the standard deviation.
Oh, okay.
So yes, but yeah. And then we've got the sample diversity issue that we just talked about. When we do this resampling, now we're piling all of our particles into just a few regions in state space. And if you're doing that, why do you need 1,000 particles or 100,000 particles, whatever the number is? If they're all essentially in just a few places, then maybe you can get away with far fewer. Yes, you're blind, but are you also throwing away clock cycles needlessly? if by using a lot of particles, if they're all essentially in just a few places. And as we talked about, well, what if other modes emerge? You may be blinded to large regions of the state space, and particularly when you're talking about the Viterbi algorithm. So, I guess on this topic, I don't have a nice solution for you. The thing that puzzles me about this is that particle filters have been so successful, even in the examples we've seen in this class. I've had a few examples where it was 6 or 7 dimensional, and particle filters didn't have any problem, even though I wasn't patient enough to use more than 100 or 500 or maybe 1,000 particles, but a relatively small number, and it worked. I mean, it still produced beautiful estimates, and I don't understand that. I don't understand fully why these work so well, given that my other previous training, before I learned about these techniques, in working on high-dimensional problems, has always told me this is hard. Like, you've got to find a trick where you somehow take a low-dimensional problem and define it in such a way that it becomes a low-dimensional problem, or linear, or something else that gets you around the curse. And in that case, we didn't do it, but something sort of magical happened here. And I've never fully understood why particle filters work so well on high-dimensional state space tracking problems. I would have predicted that they wouldn't, but I know from personal experience of myself and others that they tend to, and I don't fully get it. This is just a recap of a lot of the points we've made. Traditional particle filters are great. They require a lot of computation. The convergence proofs are for moments, but usually we don't want to use a moment. We have to resample, but if we resample, then we become blind to certain regions of the space. Works great in low dimensions, and I've updated my opinion since the first time I created these slides. It also tends to work well in higher dimensions as well. I just don't think it should. I don't understand why it works so well, and it's still nervous. One way that seemed to get around the curse of the traditional particle filters was to use a Viterbi algorithm. And I still love this algorithm. For me, for particle filters, it seems so elegant and beautiful. And the idea, I drew a diagram last time just to refresh your memory. I'll sketch a similar idea. It's not obvious, probably from the way I taught this, but if we consider a single dimensional state, and this is time in, and let's say we've just got 3 possible states that we can have, and at time 0, let's say we're examining the posterior in each of those, and then we go to the next state, and let's say there's an additional 3 states that we could be in. Each state looks at what's the most probable parent for this candidate state, parent trajectory. So this could go back further in time. And this one considers all of them, and this one considers all of them, and this one considers all of them. And we end up with the computation required at each time step is now equal to the square of the number of particles, where it was linear for traditional particle filters. So there's a big hit in computational requirements for using the Viterbi algorithm. But the big advantage is that effectively the number of trajectories that we're considering at each time step is growing exponentially with time, because this one is not only considering these 3, but it's effectively considering those 3, but each of these, if I went back one further step in time, has 3 possible parents. And so it's really 3 times 3, and if you go back one more, then it's 3 times 3 times 3. So the space that you're exploring is growing exponentially with time, along with the problem that we're trying to solve. And that's really nice that they're both growing at the same rate. Our exploration of the space, this is a very clever and efficient way of exploring the space by essentially factoring the probabilities in a clever way, so that the problem at each time step, I don't have to look at each parent separately at this time, because this one has already identified the most probable parent. And because it's a Markov property, if it's got its most probable parent, then the most probable trajectory to this state, if it happens to be this parent, will be the same parent trajectory that I chose at this time step. So that Markov property enabled us to sort of nicely, densely explore the space. There's two problems that remain. One is the computation. It's this n sub p squared computation. That means you're going to be using far fewer particles. But maybe we didn't need so many anyway. If possibly that's a consideration. So that's iffy in terms of, is that really a disadvantage or is that an advantage? Is it better to spend your cycles doing that search, or is it better to spend your cycles having more particles? I'm not sure. I think you could argue effectively either way. The second, though, is bigger, and I don't have a way around it. And that is that to get our dense grid in one dimension, it wasn't a problem. But remember, this is the dimension of the state. And if you've got a 10-dimensional state vector, I don't know how to advise you in terms of filling out that grid. You can't generate a grid. It's too big. So then you fall back on using something like the importance density and sort of guessing where the state might be based on what you knew at that time point, and creating sort of a scatter of points and hoping that you're picking some that are probable. And there's lots of heuristics you could use. I mean, one nice thing about this is that we don't care what the importance density is or how we generate the points where we're evaluating the probability. We need a lot of points that hopefully correspond to where the state actually is, or at least where the probable part of the state is. And so this sort of beats the curse, but at an expense, and you've still got this issue of you got to create your scatter of points at each time step, and you've still got a dimensional problem with the state that this doesn't overcome. So consider. And I'm sorry, I think I've already made these points. Computation, we still have to do dense sampling of the state. And we've also talked about, as much as I like this, it's giving us the most probable trajectory. It's not giving us the most probable state at the current time. Those can be different. This is giving us an entire trajectory. It does smoothing for free, which is nice. But it doesn't do that, and we also can't easily get percentiles or moments with a Viterbi algorithm. So there's trade-offs there. I mean, it's part of the reason that I'm covering it and other techniques. There isn't one technique that solves all of the problems. All right, this is a genuine solution to the problem, although it doesn't work for everything. It only works in some cases. The Kalman filter, the computation for the Kalman filter does not suffer from the curse of dimensionality. And it doesn't because we're assuming we've got a Gaussian posterior. Everything's Gaussian. The posterior ends up being Gaussian, in which case we're just trying to estimate a mean. It's a linear problem, and with linear problems you just don't suffer from the curse.
You have that matrix inversion step.
There is, that's true. And I think the order of computation scales with the cube of the dimension of the state. But I would much rather have that than exponential growth. Yeah, cubic growth is way, way better than exponential growth. But there is still, you're right, there is still an issue there. We can sometimes get the best of both worlds if your state space model can be divided such that the state is comprised of a linear portion and a nonlinear portion. And I'll explain what that means more precisely on the next slide. But let's just say for now that we can factor the state into two different components. So this is the total state vector, and now I've taken the sort of top section of that and reserved that for the so-called linear component, and then the bottom part is for the nonlinear component. And by Bayes' theorem, then the posterior of the marginal, the state now is defined as having these two components. And if I apply Bayes' theorem to this joint probability, one way that I can factor it or write it is as the posterior of the linear portion conditioned on knowing what the nonlinear portion is times the marginal of just the nonlinear portion. So you do that factoring, and if you can factor your posterior in this way, then there's some big gains that can be had by essentially using the Kalman filter to do this part and using the particle filter to do this part in potentially a much lower dimensional space where you have less problems with the curse of dimensionality. The model, generally, that I think you need to use, I think this is the most general form. So you've got three equations here. These two are the process model. This is the measurement model. The linear portion is equal to some matrix, and this matrix can depend on the nonlinear part in a nonlinear way. It doesn't matter, but there's some matrix here, so that we've got the linear part of the state is equal to a matrix that is known if the nonlinear part of the state is known, times the state at time m plus additive noise. And then the nonlinear portion can be this arbitrary nonlinear thing, just as we've had throughout the class, except this can't depend on the linear portion of the state. It can only depend on the nonlinear portion of the state and noise in any nonlinear way that you like. And then the measurement model, again, if you know the nonlinear portion of the state, then it becomes a traditional Gaussian linear model, where it's a matrix times the state vector, the linear state vector plus noise. But this is how that hybrid model is defined. And if you can fit your state space model in this form, if you can meet the constraints and express it in this way, then there's potentially big savings in computation or big gains in accuracy, depending on how you want to look at it, because we're effectively sort of beating the curse. But it's tricky, and actually it took me a long time, despite reading articles and textbooks talking about how to do this marginalization. They were never, I read them and read them and read them, and they made it sound like it was obvious, and I just couldn't get it. There was a step that I was stuck on, and I finally was able to get past that, and I'll explain what that step is in a minute. So let's assume for now that for the linear parts of the state, that the additive noise is Gaussian with known covariance matrices. And that means that the posterior distribution of the linear component is going to be Gaussian then, just like the Kalman filter. You know, the only thing here is that the nonlinear portion, if we know it, then the model becomes linear, and it's the same as the linear Kalman filter part of it. This is the same joint we had before, and if you break it up in this way, sometimes this is called the Rao-Blackwellization, or the Rao-Blackwellized particle filter. The other name that we have preferred in my lab is calling it the marginalized particle filter, where, because you're applying the particle filter to this component that is a marginal distribution because it doesn't include the linear component. So as though you integrated out the linear component of the posterior. So it's a marginalized particle filter. And again, it leverages the traditional Kalman filter for the linear portion of the state, and lots of gains to be had, memory, computation, possibly accuracy, depending on how many you're using. But it's tricky when you really sit down and study it and think carefully about what's happening here. This posterior distribution comes about as part of the linear Kalman filter recursions. You get this distribution. If you assume it's Gaussian, then we've got an estimate of what the mean is of the state. We know what the covariance is. It comes for free as part of or it's just part of the recursions that you do. So we've got that. We know what that is. And then you look at this, and so I need that also. If I'm going to get the overall posterior, then this isn't enough. I also need to know what this is, and I have to think about that. But it turns out that that's hard, and it's much harder than what we experienced previously. And the reason for that, I think, is explained by these equations. So here I'm getting to the term we're interested in. This is the term that we want. It's a nonlinear portion of the state conditioned on odd observations up to the current time. And as before, I can create an arbitrary probability over here and then factor it a couple of different ways to then solve for what I want. So this joint can be written as a product of these two terms and apply the Bayes theorem this way, or I can do it this way. Just two different ways of doing that. Where here I'm conditioning on the first term, or I'm conditioning on y of n, and writing this as the conditional, and this is then the marginal of what's left. And this is doing it the other way around, where I write this as y of n conditioned on the nonlinear portion of the state, and then this component. And then we go down one step, and I'm doing Bayes' theorem again on this term. So I'm writing this as the nonlinear portion of the state of time in, conditioned on the past, and the past, this should be conditioned on y of 0 to n minus 1. I apologize for that error. Yeah, that should be conditioned on. I made a mistake there. With our nonlinear model, as before, because it is of the Markov property, if we know what the entire past nonlinear portion of the state is, then this is just equal to the state of time n conditioned on n minus 1. Same thing we've done before. But what we can't do is do the same thing to this term. That's what we've lost. And I'll say more about that on the previous slide. And here I finally converted my comma into the vertical line as I should have. So same equation that was at the bottom of the slide before. And this is the term that's now troubling. Before, because of the Markov property, we know that if we know what the state is, then this became the likelihood function before. You know, probability of y of n given the state plus all the past observations is just equal to y of n given the state, because the state completely determines statistically what the observation is. But now I don't have the state. I've only got part of it. I don't have the linear part of the state. This is not what we had before. This is not the likelihood. This is something different. And that screws everything up.
You specified that the nonlinear portion could depend on the linear portion.
That's true, but the measurements depend on both. Yeah, so before we did, if I had the full state, then this would become the likelihood that we've worked with throughout the term. But it's not. It's not that. What we've got is this, and this is not equal to that. So, this is where I was scratching my head, and I'd read the papers and reread them, and they'd be like, oh, it's obvious, and move ahead, and I couldn't figure out what they did at that step. I was very confused by it. And the insight that I had after mulling this over with my PhD student is that although we don't know what the linear state is, we do have an optimal linear estimate. And that optimal linear estimate only depends on the nonlinear portion of the state and all the past observations. So if this probability conditioned on x of n and y of 0 to n minus 1, I could also condition that on y of n, the nonlinear portion of the state, this, and the past observations, because this can be calculated from those two. I haven't really changed anything here. This is a function of those two things. And it turns out that this is something that we know is part of the common filter recursions. We calculate a y hat, and it's a function of the estimated nonlinear portion of the state. And we've got this error, this difference between those two that are the innovations. And with that, you actually know then what the distribution is, or what the distribution is of y of n conditioned on these things. If we know the distribution of the residuals, then we know actually what the distribution is of the state, just like we did earlier. This turns out to just be normally distributed with the meaning that we can calculate. If we know what the nonlinear state is, and we've got our linear estimate of the state, this is normally distributed with that mean, and we know what the innovation error covariance is because it's calculated as part of the common filter recursion. So we actually have that term and can calculate it as part of the recursion. So this is what you use for that element to get that posterior that you need. And then with that, you're off and running. You can do all the things that we've talked about doing. It becomes relatively straightforward once you've got that. There's a lot of math and a lot of memory. I've got an example here. I won't, in the interest of time and knowing that we've got some more things that we want to hear, I won't dwell on this, but this is the frequency tracking example, where if we've got an electrocardiogram, the electrical measure of your heart, is a quasi-periodic signal. Your heart beats roughly once per second. And if you look at that signal, it's almost like an impulse train. Impulses are broadband. So if you represent that as a Fourier series, then you've got like 70, 80 harmonics, a very large number of harmonics. And if you're trying to do that with a particle filter, you've got particles trying to cover all these linear coefficients that in some sense are unnecessary. We've got the sort of bias or the trend, and then we've got all these coefficients, and the only nonlinear portion really is the phase and maybe the frequency. And so in this case, you could have a very small nonlinear particle filter and use your Kalman filter to estimate the coefficients and estimate the trend much more efficiently and without running into this problem. So that's one example where this works really, really well. And we've gone over this, dwell on this now. There's one other idea that I want to get across. We've run into integrals or discrete time approximations of integrals before. We've done it actually many times in this class. So here we've got the frequency, there's a random walk model for the frequency, and the phase is just an integral of that frequency. And again, we're talking about things that are at the edge of my knowledge. I don't know if it's really necessary to estimate the phase as part of your state. Because this is a function of a random variable, and it's got memory to it, but there's no extra noise term here. And so arguably, even though this is nominally of dimension 2, since this is a deterministic function of this random variable, you could argue that the dimension of this state vector is effectively 1. I'm not sure. I'm still a little bit torn on it because there is an issue. Well, if it's an integral, what about the offset? What about the initial phase? Maybe you need a bunch of particles to cover a lot of random phases because you don't know how the thing started. It kind of comes back to what you were talking about, Reed. So maybe you need that. But in this particular application, that's probably not true because the coefficients also can represent a constant phase. So even if you said the phase was 0 for every particle, and then just integrated it directly, but not as part of the particle filter, outside the particle filter, and maybe your particle filter is only single dimensional, effectively. You could do it that way, maybe. Jamie?
What if your measurements depend on that integral?
Yeah, I've been thinking about that as well. And you would still, whether this was done within the particle filter or outside of the particle filter, you would still be, I think it would turn out to be equivalent because for each particle, this is just going to integrate whatever the frequency is. And that would be true whether you did it inside or outside the particle filter. And the measurement is a function of the phase, not the frequency. Each given time step, it's a function of whatever the phase is, not the frequency. But whether you do it inside the particle filter or external to it, I think it would turn out to be identical. I don't think it would make any difference. I think. So, I'm not taking the time to give you another MATLAB example with a lot of plots of the posterior, but I think in this case, it's not necessary. I mean, I could show you, hopefully we'll see from Jeff, we see, the particle filter does the same thing if you have enough particles as the linear Kalman filter recursions, but these recursions are far more efficient computationally. I think you can grasp that idea without going through a concrete example. But the main point on this set of slides of marginalization is if you can get your state space model in this form, then there's potentially large gains to be had by blending the Kalman filter recursions with the particle filter recursions, whatever flavor you're using. So it's something you should be aware of. It's another tool possibility for the things you guys are working on. And I'm not going to talk about this because I'm not actually persuaded it will work, and I want to save time.
Just a quick question about that. From the way that's written, it seems like you would be supposing a unimodal state, or is that?
Not for the nonlinear portion. The nonlinear portion could still be multimodal, but when you're talking about the linear part of the state, it is you're driving a linear process with Gaussian noise, unimodal noise. It will be Gaussian and unimodal.
I should rephrase, because I mean to say that the measurement can't have ambiguity, because it's just, even though the matrix can depend non-linearly on the state, you still, you're just multiplying the matrix by the state in the end.
For multiplying the matrix times the linear part of the state.
Oh, okay.
Yeah, only the linear part of the state. And I mean that could also be a constant. So you could have a function of the nonlinear part of the state plus or not part of the linear portion of the state. That's possible. Just, I guess, general bottom line advice. When you can use the Viterbi algorithm, take this with a grain of salt. Practical experience suggests that particle filters with resampling and with the tricks we've talked about still work even in high dimensions. There's limitations, but they still work. They don't just completely die due to the curse of dimensionality. Nonetheless, it's a good principle generally to keep your models as simple as possible, keep the dimension of your state as low as possible. I didn't really go over this, but one of the other general ideas that's generally good is to try to keep your state variables as statistically independent of one another as possible. And again, we didn't really go over that, but the idea is rather than having them tightly coupled, or if this state moves, this one's got to move with it, it's much better if this one can move sort of independently of this one and they're not tightly coupled to one another. So for example, in the frequency tracking example, representing it in the trigonometric form where you've got a coefficient for the cosine and a coefficient for the sine works better than if it's amplitude and phase, where the amplitude has got to stay within a certain range and may be related to the phase. That doesn't work as well. It's also more nonlinear. But generally, try, when you're designing these, you want like the biases to be statistically independent of one another as much as you can. And marginalization can help a lot, especially if you're running out of cycles or you've got a thesis deadline looming and you can't wait another week for your particle filter to finish running. This could really speed things up. So that's it for this set of slides. So let's take a 5-minute break, and then Reed, I'll have you go, and then Jeff, we'll see what you guys have, and then we'll call it a day. So we'll take a quick 5 minutes.
And I can use your iPad for homework 4. Homework 5 didn't want to upload.
Okay.